This is Lecture 7C for Calculus 2 on trigonometric substitutions. In substitution, we are used to substituting a single variable for a trig function. For example, we might substitute u for the sine of x. And that makes things get very simple. If we put this in an equation such as the one right here, we end up with a polynomial in u which we can solve. Okay, but now we're going to go the other direction. We're going to substitute a trig function for a single variable. Initially, this seems like it's going entirely in the wrong direction, but it isn't. Things do get simpler, and you're able to solve certain integrals. There are three forms that call for this kind of substitution, and they're listed here. Square root of a squared minus x squared, square root of a squared plus x squared, and the square root of x squared minus a squared. You encounter these forms often when you're trying to compute the area of various conic sections. So these forms, although they look very specific, they do occur in integrals. Each one of these forms has its own substitution rule, and then when we use the substitution rule, we get rid of the square, we get rid of that plus or minus sign, and we get rid of the square root. So that's a simplification. Okay, so here we're going to go through those three forms again. I'm going to show you the substitutions. Here's the first form, square root of a squared minus x squared, square root of a squared plus x squared, and the square root of x squared minus a squared. So going back to the first one, we'll go through the substitutions. For the first form, the substitution is x. Remember, a single variable gets replaced by a trig function. So it's x equals a times the sine of theta. A is a constant. In the second form, we substitute a tangent theta for x, and in the third form, the substitution is x equals a secant theta. Okay, and I'm going to go back to the top here and show you how this does simplify. Alright, so we're working here with the square root of a squared minus x squared. We substitute the a squared, x squared is then a squared sine squared theta. You can factor out the a's, and you end up with 1 minus sine squared theta, but using the Pythagorean theorem for can't switch pins. Okay, so we use the Pythagorean theorem, cosine squared theta plus sine squared. That's weird. I still can't figure out why this pin doesn't write, so I constantly talk about it. Okay. Right. Using that, we can substitute 1 minus sine squared theta, we can substitute cosine squared theta. Taking the square root, we end up with this, a cosine theta. In other words, we lost the square, we lost the negative sign, and we lost the square root. Let's look at the second case. We have a squared plus x squared. X is a tangent of theta, so here we have a squared tangent squared theta. Again, factor out the a's, we're left with 1 plus tangent squared theta, which is secant squared theta. It's just the other form, of course, of this Pythagorean theorem. If you divide this by cosine squared theta, you remember this from trig. Here's cosine squared theta, and divide this side by cosine squared theta, then you end up with, of course, 1 plus tangent squared theta equal to secant squared theta. And that's an equal sign. There it goes. All right. Now we can take the square root of secant squared theta, and we get a secant theta. Again, in this case, we have lost the plus sign, a square, and the square root. Third case is similar. Substitute a squared secant squared theta, end up with secant squared theta minus 1 after a is factored out. Use the same identity here, and you end up with a square root tangent squared theta, which gives you a tangent theta. And that is the substitution rule. There's a little more to the rule, of course, since we have to specify what theta is. If we end up with theta in the answer, well, let's just solve for theta. Theta is then the arc sine of x over a. So arc sine is restricted to this principal value, minus pi over 4 to pi over 2 to pi over 2. So we restrict theta in the substitution to lie between minus pi over 2, which I guess we put a minus sign there, and to pi over 2. Right. And for the tangent function, we make the similar restrictions. And these are actually, and I look at it, I don't see any reason these are not less than or equal to, so I'll add that here on these slides. For secant, if you remember, there are branches of the secant function, or the arcsecant, so the conditions are a little more complicated. If x over a is less than or equal to 1, then secant lies between 0 and pi over 2, and that is a strict inequality. And if x over a is less than negative 1, then theta lies between pi over 2 and pi. Once the substitution is made, you can carry out the integration. If you have a definite integral, you simply evaluate it with the proper limits. Of course, depending on your substitution, you have to take the limits, change the limits of integration. But if you have an indefinite integral, then you have to reverse the substitution, and that isn't as straightforward as it is when you substitute a single variable for a function. For example, if you made this substitution here, u equals sine x, then every instance of u in the answer is just replaced by the sign of x. That's it, you're done. Here, it's harder. If you, as you recall, if you integrate trig functions, you usually end up with other trig functions. If you have a complicated, say, integram with many trig functions, you're going to end up with all kinds of trig functions at the end, including the angle itself, possibly. And those will have to be reversed. So you're not just reversing the first substitution, you're reversing integrals, trig functions that resulted from the initial substitution. That was a lot of words. Okay, let me show you how you do it, and then it will be clear. The way we reverse all those trig functions that we might have in our final answer, we do the triangle procedure from trigonometry. If I start right here, and let's take this one. Here's a substitution: x equals a sine theta. All right, that means that the sine of theta equals a over x. All right, so I can write this like, I'm sorry, it doesn't equal that at all. It equals x over a. All right, so if the sine of theta equals x over a, then I know that x has to be the opposite side, because sine is opposite over hypotenuse. So x, whatever x happens to be, is going to be the opposite side from the angle, and a is the hypotenuse. Then I can use the Pythagorean theorem to determine the value of the adjacent side. We do the same thing here. If x equals a tangent theta, then the tangent of theta equals x over a. So tangent is opposite over adjacent. That means the opposite side has to be x, and the adjacent side is a. You can use the Pythagorean theorem to find that the hypotenuse is the square root of a squared plus x squared. And if you have a secant theta, you can do the same procedure there too. Okay, so by constructing these triangles, then we can reverse any trig substitution by just referring to the triangle that we constructed. Here's an example. We're going to calculate the area of a quarter circle or of a quarter ellipse. We can just do this in general. So here's a general expression for an ellipse or a circle. X squared over a squared plus y squared over b squared equals 1. If a equals b, of course, it's a circle because that is the radius. If a is not equal to b, then we have an ellipse. All right. Let's rearrange this and solve for y, and we end up with y equals, we're going to look for first quadrant, so we don't have to worry about signs right now, b over a times the square root of a squared minus x squared, and x lies between 0 and a. All right, this is that form, the first form that calls for a trigonometric substitution, and of course we use x equals a sine theta, because to find the area we have to integrate, so we use x equals a sine theta. Remember, dx is a cosine theta. All right. We have to change the limits of integration. When x is 0, theta is 0. Fine. When x is a, theta is pi over 2. So now we'll be integrating from 0 to pi over 2. This makes sense because if we're looking in the first quadrant, we expect that the area will, the angle will move from 0 to pi over 2 as we trace out the edge of the circle or the edge of the ellipse. So this is the substitution that we'll use. So here again is our integral for the area. It includes the form square root of a squared minus x squared. We make that substitution that x equals a sine theta. We have to square it and put it here. And then dx ends up, by carrying out the differentiation, we end up with a cosine theta as a substitute for dx. Right. Factor out the a, and then use the substitution that 1 minus sine squared theta is cosine squared theta. Take the square root, and this is what we did on the second slide. So we know that. We also know this. We also have this term from the derivative. Okay. Factor out the a, and now we're working with cosine squared theta. You can remember from trig integrals how to handle this. We can use the identity, the half angle identity, cosine squared theta equals 1/2 times 1 plus cosine of 2 theta. I substitute that, and now this is all I'm left with that I have to integrate. So what was a very seemingly impossible situation at first has become something that it's very easy to integrate. Okay, we can go ahead and integrate this, and here's our solution, and we're going to evaluate it between 0 and pi over 2. So we carry out the integration, and the answer is pi times a times b for the ellipse. Now for a circle, what happened? Oh, I know I didn't mean that at all. Okay, well, I don't want to do this lecture over again. I'm just going to fix my error. Okay, what I have here is pi ab over 4. The reason I put that is to say if I wanted the whole ellipse, I would multiply by 4. But if I carry out this evaluation, I end up with pi times a times b over 4. That's for the ellipse. Now in a circle, a equals b, and that's the radius, so I can substitute r for a and b, and I end up with, for a circle, pi r squared over 4, which is the expected results for a quarter of the circle. That was carrying out this integration for the definite integral. Now let's look at the reverse substitution that we would have to do for the indefinite integral. If this was an indefinite integral, our final form here with the substitution in place is a times b over 2, fine, times the quantity theta plus 1/2 sine of 2 theta plus whatever, the constant of integration. Right. The substitution that we used was x equals a sine theta. Theta is the arc sine of x over a. So we've already reversed now. Immediately we've reversed the theta. Now we have to reverse the sine of 2 theta. To do that, we'll use the trig identity again. The double angle sine of 2 theta is 2 times sine theta cosine theta. So all we have to reverse is sine theta and cosine theta. That got rid of the 2 theta complication. Now the sine of theta is x over a. And for the cosine of theta, what we would do is go back to that triangle. I'm going to show you that right now. So here are those triangles again, and we're looking at the middle triangle because our substitution was x equals a sine theta. So if I have the cosine of theta is adjacent over hypotenuse, so that would be the adjacent is square root of a squared, this means adjacent, not a squared minus x squared divided by a. That is reversing the substitution here. With cosine theta, its reverse is square root of a squared minus x squared over a. And remember, we also had a term that was sine theta, so sine theta obviously is x over a. So here we are back at the last slide again. This is the one we went to before we looked at the triangles. And I know all the yellow and everything's been taken off. All right. So what we're trying to do is reverse the substitution here, sine of 2 theta. Sine of 2 theta we wrote as 2 sine theta cosine theta. By our substitution, sine of theta is x over a. Cosine theta by that triangle was the square root of a squared minus x squared over a. We can put all that back together, and here is our answer. All right. This is for the indefinite integral. And now you see there's no thetas. We have the answer in terms of x and a, which were our original variable. X was the original variable.